Have you ever felt like there's some kind of hidden force at work inside your electronics? Something that's just silently killing performance, causing systems to fail, and costing a fortune in downtime and repairs? Well, you're not wrong. And today, we're going to unmask this invisible saboteur. It's a question that keeps engineers and facility managers up at night, right? You specify all the right components, you build the system exactly to spec, but it still underperforms. Capacitors are burning out, terminals are overheating, efficiency just plummets. So, why does this happen? Okay, let's dive right in with a number that should really grab your attention. A recent IEEE study found that up to 35% of energy losses in certain high-frequency power conversion systems, well, they can all be traced back to one single root cause. That's right, over a third of the energy just wasted in these absolutely critical systems is because of one single, kind of sneaky physical effect, an invisible saboteur that most people don't even think to look for. So let's be really clear here. This isn't just some minor technical quirk we're talking about. This is a widespread and incredibly expensive problem, and it's hiding in plain sight inside our most advanced electronic systems. So what is this hidden villain? Well, it's a fundamental principle of electrical engineering known as the skin effect. Let's pull back the curtain and see exactly what it is, and more importantly, how it works. Okay, so in the simplest terms, when you run AC power through a wire, especially at high frequencies, the electricity doesn't actually use the whole wire. It kind of gets lazy and decides to just travel along the outer surface, or you could call it the skin. Now, what's really interesting is how this actually happens. As that alternating current, or AC, flows back and forth, it generates this changing magnetic field. This field then creates these tiny swirling currents inside the conductor. We call those eddy currents. And you can think of these eddy currents as creating a sort of internal traffic jam. They literally oppose the main flow of electricity, pushing it out to the conductor's edges. And this right here perfectly illustrates the consequence. At high frequencies, your solid copper bar might as well be a hollow pipe. You're paying for all that copper in the middle, but the electricity isn't even using it. It's just dead weight. So what's the real-world impact? Well, it all comes down to resistance. Just look at this chart. A conductor with a tiny direct current, or DC resistance, can see its AC resistance absolutely skyrocket by 15 times or even more at a high frequency like 1 megahertz. And you know what more resistance means? More energy wasted as heat. And that is where the real trouble begins. Now, all that excess heat, it has to go somewhere, and it often targets the most vulnerable components in a system. Let's take a look at how this quirky physical effect spirals into a component-destroying nightmare, focusing on capacitors, which are really the heart of so many power systems. So the skin effect dramatically increases a value that engineers call equivalent series resistance, or ESR. The simple way to think about ESR is as a tiny, unwanted resistor that's hiding inside your capacitor. As that high-frequency current flows, this hidden resistance generates heat, basically turning your critical component into a little space heater. And hey, this isn't just a theory. Here's a real-world case from a water treatment facility. Their massive variable frequency drive was just burning through capacitor banks in under a year. The expected lifespan was supposed to be over 5 years. The costs and the downtime were just staggering. And here is the smoking gun. A thermal camera showed that the capacitor terminals were hitting 95 degrees Celsius. That's 203 degrees Fahrenheit. That is some serious heat, all generated by the high resistance from the skin effect. It was literally cooking the components from the inside out. The fix was actually both simple and brilliant. They just replaced the solid copper bus bars with thin laminated copper sheets. And look at these results. The temperature dropped by a full 30 degrees, and the expected lifespan shot right back up to where it was supposed to be. This one change saved the entire system. Okay, so now that we understand the enemy, how do we fight back? Well, fortunately, there are proven industry-standard strategies to mitigate the skin effect and protect your systems. So the first line of defense is choosing the right conductor. As we've seen, solid bars are just incredibly wasteful at high frequencies. The solution is to use specialized conductors, things like Litz wire, which is basically a cable made of tons of tiny, individually insulated strands, or those laminated bus bars from our case study. Both of these designs force the current to distribute itself evenly, using the entire conductor and dramatically cutting down on losses. But solving this really requires a multifaceted approach. It goes beyond just the wiring. You also have to specify components that are built for the job, like the low ESR capacitors we're going to talk about in a second. And your actual circuit board design matters too. Keeping electrical paths short and wide helps minimize resistance. Using multi-layer boards with big dedicated power planes gives the current a much better path to follow. And finally, of course, none of this works without proper thermal management to whisk away any heat that does get generated. Now, you might be thinking, okay, these optimized components, they sound expensive. And you're right, the upfront cost is higher. But the crucial thing here is to think about the total cost of ownership, because the payoff can be absolutely enormous. So let's look at another case study. This one's from a solar farm. They had a choice. They could go with budget capacitors for $800 a unit, or they could pick premium low ESR ones for $2,400. Now, on paper, the budget option looks like a no-brainer, right? But just look at what happens over 5 years. The budget capacitors failed constantly. When you factor in the cost of all those replacements and the lost revenue from downtime, the total cost just becomes astronomical. The premium capacitors, which didn't fail, were vastly cheaper in the long run. So what was the final tally? By investing in the right components up front, this solar farm saved over $1.2 million in just 5 years. That's the power of understanding and designing for the skin effect. And that brings us to the final crucial question. Now that you know what to look for, the unexplained heat, the premature failures, that nagging inefficiency, it's time to ask, is this invisible saboteur hiding in your system too?